Hello, everyone. So today we're going to look at therapeutic applications of laser. Before getting into the topic, we'll have to first know what is laser. So laser is nothing but it's just light amplification with stimulated emission of radiation. We might have studied about laser in our earlier classes, but we'll just quickly go through some of its characteristics. The first one is coherence. Coherence says that every single ray of the laser is parallel with each other. That is from the beginning to the end. Collimation states that uh, the laser rays are in phase and non-divergent. Monochromaticity is a phenomenon by which every ray the laser has the same wavelength. Wide range of pulse structure. We can design the laser in such a way that can form like any sort of pulse structure that is necessary for us. Uh, like we saw with the principle of laser, high power states that laser has like very high energy. Moving on to the components of laser, the first thing we see is the lasing medium, which provides appropriate transition and determines the wavelength. Some of the examples are given over here. Next one, we see pump, which provides the necessary energy for population inversion. An electric discharge lamp, a flash lamp, or even another laser can be used as the pump. Cavity, which provides the opportunity for amplification, produces a directional beam. Here we see like two mirrors. Uh, one is completely reflecting, the other one is partially reflecting. The electrons from the pump, they reflect back and forth between these mirrors so as to form this collimated, coherent laser beam. Interaction between light and tissue is a really important topic which we'll have to know before moving on to therapeutic applications of laser. When laser light falls on the tissue, like five of one of these five things can happen. That is reflection in the sense that it can fall and can reflect. We can, if you see over here in this image, uh, the light can fall and can reflect back. Or refraction. Refraction is it changes its direction. Like it does not pass through the object, or it doesn't completely reflect, but it just changes its direction when it falls on the tissue. Absorption, uh, the light gets absorbed by the tissues. Fluorescence is nothing but it creates light or it irradiates the cells so that when viewed from another viewing object, it glows. Scattering, it just follows some random path and it either gets absorbed or it comes out the tissue. So this interactions depends on the constituents of the tissue, the optical properties of the tissue, and the propagation of light. We'll be looking into two main interactions between light and laser, I mean tissues. One is absorption and the other one is scattering. So in absorption, what happens is the extraction of energy from light by a molecular species. With diagnostic applications, the transition between two energy levels of a molecule that are well defined at specific wavelengths could serve as spectral fingerprint of the molecule. Various types of chromophores in tissue, wavelength-dependent absorption, tumor detection, and other psychological assessments are like few of the diagnostic applications of laser. In case of therapeutic applications, the absorption of energy is a prime mechanism that allows light from a source to produce physical effects on tissue for treatment purposes. We might have heard about LASIK. It's a surgery, eye correcting surgery, that is the retina correcting surgery. So that follows the principle of absorption applied to human tissues. Even for tattoo removal and PDT, this principle of absorption is being used. But there are two main parts of the human body that does this thing of absorbing. One is hemoglobin, the other one is lipid. Hemoglobin, as we all know, it is responsible for oxygen transport, and lipid is nothing but the fat. So these are the two uh, types of tissues in human body that undergo absorption when laser or like any sort of light falls in it. Scattering is nothing but change of direction of propagation and or energy of light by a molecular species. That is nothing but the human tissues. So scattering depends on size, morphology, and structure of the components in tissues. Example, we have different types of lipid membranes, collagen fibers, nuclei, etc. Variations in these components due to disease would affect scattering properties, thus providing a means for diagnostic purposes. That is, if say there is a healthy tissue, that would have a different type of scattering property. But if that is affected by some sort of disease, then the scattering pattern would be different. So in that way, we can diagnose these applications. And coming to therapeutic applications, scattering signals can be used to determine optical light dosimetry, provide useful feedback during therapy. So when a laser gets absorbed by certain uh, cells or tissues, we can observe the uh, scattering. That is, it, see from here you can see like the difference between purely absorbing medium and a medium that scatters light. When it comes to scattering medium, the Lambert viola does not apply. One of the practical application of the diagnostic feature of laser is optical or fluorescence spectroscopy. The goal here is to learn something about the tissue. It's a non-invasive tissue characterization to replace or guide physical biopsy. It is used in the early diagnosis of lung cancer. So the main principle of optical or fluorescence spectroscopy is two images are acquired at two wavelengths. A ratio image is computed and displayed to the physician in real time. The application uses coherence and collimation, the two properties of laser which we saw earlier, to achieve the efficient coupling to the fiber and endoscopic light delivery. In addition, the choice of laser, that is the helium cadmium, provides optical power at optimum wavelength for the fluorescence excitation. So this excitation can be viewed in the monitor that is attached to the image processor, which is in turn connected to the cameras, that is the sensors, which combine the two captured images and gives us the output of the display monitor. So another therapeutic application of laser is the photodynamic therapy. The goal here is to modify the tissue, that is, kill malignant cells. It uses chemical reactions initiated by light absorption to kill cells. Originally, the application uh, was specific to oncology, but it is also applicable to other diseases, including age-related macular degeneration, which is caused by proliferation of new blood vessels in the retina. The process is a three-step process. The first one is to inject the photosensitizer, or it can either be applied topically, that is on top of the skin. As you see in the image, we have the epidermis and dermis, and the abdominal blood vessels are present in the dermis. We'll wait for the photosensitizer to distribute itself through the region that is needed to be like therapeutically operated. The next step is to irradiate with light of appropriate wavelength. So what this light does is, we already have the photosensitizer, and when this light falls on the photosensitizer, it destroys or kills magnet cells. And that is it for the therapeutic applications of laser. See you next. So bye bye.